The Kármán vortex street is one of the most striking images in fluid dynamics. As a fluid flows past an obstacle, swirling vortices are shed periodically. I'm Jeff Chasnov, and I'm a professor of mathematics. In this video, we're going to have a close look at the flow around a circular cylinder. Laboratory experiments have been performed, and so have numerical computations. Flows past obstacles also occur in nature. The Kármán vortex street has been observed in atmospheric flows when the wind blows over oceanic islands. The phenomena of vortex shedding can also cause weird behavior on your local highways. The ancient Aeolian harp sings its melancholic tune because of vortex shedding and the Kármán street. Here is a particularly large and beautiful harp near the famous Exploratorium in San Francisco. The Kármán vortex street is named after the pioneering aerospace engineer Theodor von Karman. Von Karman was born in Budapest in 1881 and immigrated to the United States before the Second World War. He was among a prominent group of Hungarian scientists who contributed to the American war effort. The joke was that this group spoke a strange foreign language and came from a little-known country. With superhuman intelligence, perhaps they were actually descendants of extraterrestrials, and thus they became known as the Martians. In 1963, then-President John F. Kennedy presented von Karman with the National Medal of Science.
Gentlemen, Dr. von Karman, it's a great pleasure for me to select you as the first recipient of the National Medal of Science. This nation, and indeed the entire free world, holds you in the highest esteem and respect for your devoted service, for your scientific achievements, and for your warmly human gifts as a teacher and counselor. Your assistance to the United States Air Force and to the NATO Advisory Group for Aeronautical Research and Development have been outstanding. It is hard to visualize what the world would be like without aircraft and jet propulsion, or without the vision we have just entering the realm of reality of exploring space. I'm especially glad to present this first National Medal of Science to one of the pioneers who has helped make all of this new and exciting age possible.
Von Karman may have pioneered our understanding of aeronautics and astronautics, and we've become quite good at building airplanes and spacecraft. Yet fluid mechanics remains a difficult subject. The governing equations are nonlinear partial differential equations called the Navier-Stokes equations. Analytical solutions of these equations exist only for very simple flows, so we need to solve these equations numerically, often using supercomputers. In their simplest form, these equations contain one dimensionless parameter called the Reynolds number, Re, named after Osborne Reynolds, who in the late 1800s established the condition in which fluid in pipes transition from a laminar smooth flow to a turbulent chaotic flow. We know that low Reynolds number flows are laminar and high Reynolds number flows are turbulent. In an often repeated story, we're told that the German physicist Werner Heisenberg, one of the founders of quantum mechanics, said on his deathbed, "When I meet God, I'm going to ask him two questions. Why relativity and why turbulence? I really believe he'll have an answer for the first." The Kármán vortex street at low Reynolds numbers is a periodic laminar flow, yet there is no simple analytical solution. Even the zero Reynolds number flow past a cylinder, the polar opposite of turbulence, is a very difficult problem to solve. George Stokes tried to find a solution in 1851, and his results are now known as the Stokes paradox. You can't solve this problem by simply setting the Reynolds number equal to 0, because the resulting equation, together with its boundary condition, doesn't have a solution. Asin modified Stokes' equations in 1910 and was able to provide a good approximate solution. The analysis of the Karman street came soon after. Von Karman writes, "In 1911, I was a graduate assistant in Göttingen, working with the physicist Ludwig Prandtl. At that time, Prandtl's main interest was in the theory of the boundary layer, the flow of a fluid very close to the surface of a body. Prandtl had a doctoral candidate, Karl Hemans, to whom he gave the task of constructing a water channel in which he could observe the separation of the flow behind the cylinder. The object was to check experimentally the separation point calculated by means of the boundary layer theory. For this purpose, it was first necessary to know the pressure distribution around the cylinder in a steady flow. Much to his surprise, Hemans found that the flow in the channel oscillated violently. When he reported this to Prandtl, his mentor told him, "Obviously, your cylinder is not circular." However, after very careful machining of the cylinder, the flow continued to oscillate. Then Hemans was told that possibly the channel was not symmetric, and he started to adjust it. I was not concerned with this problem, but every morning when I came in the laboratory, I asked him, "Herr Hemans, is the flow steady now?" He answered very sadly, "It always oscillates." So von Karman went home for the weekend and worked out the stability of an arrangement of vortices and determined that the vortex street was the stable configuration. Von Karman never claimed to have discovered the street that was named after him. He mentions a fresco from a church in Bologna, Italy, where St. Christopher is shown carrying the child Jesus across a flowing stream. Behind the saint's foot, the painter drew alternating vertices that resembles a Karman street. The vertices were also observed earlier by a French professor, Henri Bernard, now well known for Rayleigh-Bernard convection. Von Karman claims that Bernard was very jealous about the naming of the vortices, so von Karman told him, "I agree that what in Berlin and London is called Karman Street, in Paris shall be called Avenue de Henri Bernard." And von Karman claims that after that wisecrack, they made peace and became good friends. Back in 1982, when I was still a student, Milton Van Dyke published his book, An Album of Fluid Motion. Here's a copy from our library. You can see the von Karman street on the cover, and there are many visualizations of the street in the book. This ensured the popularity of the street in the fluid dynamics community. Nowadays, with fast computers and commercial software, students are able to simulate the von Karman street in their engineering courses. Some adventurous students may even try to write their own codes. A two-dimensional simulation may start with the Navier-Stokes equations for the stream function and the vorticity in log polar coordinates, the obstacle, and a finite difference grid. The equations are discretized and a numerical scheme is chosen. Sounds easy? Well, the numerical scheme needs to be stable and efficient, and the code needs to be bug-free and fast. Still not an easy problem, so most students use package software, like OpenFOAM or ANSYS Fluent. I wrote my own codes and can show you some of my solutions. It's easy to visualize the stream function and the vorticity of the fluid using color and contour lines of constant values. In a steady flow, the contour lines of the stream function show us the direction of the fluid motion. You can literally see how the fluid flows by simply following the contour lines. The vorticity shows us the local spinning motion of the fluid. It's a bit harder to interpret, but we'll see that for an unsteady flow, the vorticity will give us the best visualization of the Kármán street. Let's start with the zero Reynolds number flow. Here's a plot of the stream function, and here's a plot of the vorticity. The fluid moves from left to right, and yet the flow fields are symmetrical upstream and downstream of the cylinder. This is a special feature of the zero Reynolds number, and it's not a realistic flow. Let's first look at the stream function as the Reynolds number increases from 0 to 6. The streamlines shift to the right as the fluid particles get displaced a larger distance behind the cylinder than in front of it. And if we look at the vorticity, we see it's being swept behind the cylinder as the Reynolds number increases. The fluid is spinning more behind the cylinder than in front of it. Something new and interesting happens when the Reynolds number becomes larger than around 6. Here's what the stream function looks like for a Reynolds number of 10. We now see two attached eddies in the flow behind the cylinder. If we draw arrows on the streamlines to denote the direction of the fluid flow, we can see that the fluid in the upper eddy must be rotating clockwise, and the fluid in the lower eddy must be rotating counterclockwise. The fluid is trapped in these attached eddies, recirculates, and never moves off downstream. We can see how these recirculation regions grow as we increase the Reynolds number. Here's a video of the stream function as the Reynolds number increases from 6 to 50. And here's a video of the vorticity. The most prominent feature here is the vorticity that comes off the front of the cylinder and extends into the flow behind the cylinder. At these Reynolds numbers, the flow is still steady. The fluid is moving, but its direction and its speed is always the same. These were the steady flows that Prandtl and his postdoc were trying to find. The steady flows at higher Reynolds numbers become unstable. Unstable flows are not seen in nature because they're unstable. They're replaced by stable flows. Let's have a look at how a steady flow at a Reynolds number of 45 becomes unstable as we increase the Reynolds number to 60. First, we develop the steady flow at the lower Reynolds number of 45. This is what we would see in an experiment as we turn on the water flow in a channel. We then raise the Reynolds number to 60. In an experiment, we would increase the flow rate and the velocity of the fluid. We see that an oscillation begins to develop, and the vorticity eventually breaks up. The resulting flow is a rather damped Kármán street. The flow is no longer steady, but we see that it's periodic. Now let's lower the Reynolds number back down to 45 and see what happens. The oscillations slowly die down, and we see that the flow returns back to its steady state. Those of you who know some nonlinear dynamics, this sudden transition from a steady flow to an oscillating flow is called a supercritical Hopf bifurcation. If you're interested, you can look up the mathematics on the web. Experiments have estimated that this transition occurs at a Reynolds number of around 46. Let's look again at the Kármán street when the Reynolds number is 60. We can zoom into the vorticity field near the cylinder. We can see the attached eddies oscillating with the vortex street, but they don't seem to interact with the vortex shedding. This dynamics changes slightly at higher Reynolds numbers. Let's first compute the flow field at a Reynolds number of 105. Again, see the flow field develop, become unstable, and form a Kármán street. Now if we zoom into the attached eddies, we can see them interacting with the street, something that wasn't obvious at the lower Reynolds numbers. What happens at even higher Reynolds numbers? Turbulence, of course. Turbulence is a three-dimensional instability, and I don't have the software or the computer firepower to simulate three-dimensional turbulence. So let's have a look at some of the videos that I could find on YouTube. Here's a developing turbulent flow at a Reynolds number of 3900. And here's the flow field right next to the cylinder. Here's another beautiful visualization of a turbulent flow and a Reynolds number of 2200, but around a square cylinder. Let me conclude with a beautiful clip of an airplane coming into land and shedding two absolutely gorgeous vortices. I'm Jeff Chasnov. Thanks for watching.